learners. Today we're going to be talking about water and all the different ways it's important for us. Alright, so the first cool quality we get to talk about is how water is a universal solvent, which means the solvent is the thing that can do the dissolving. It's a longer word and you need more of it than you need solute or solute. So that's the thing being dissolved. So like if we were filling a hummingbird feeder, this would be water and this would be sugar, and together it would make a solution. So in this case, this is so for this example, this would be water, this would be salt, and we would get salt water. But it doesn't have to be a solid, it can be a liquid or a gas, so think like the carbonated beverage of your choice. Your solvent is still water, your solute is all the sugars and the bubbles, the carbon dioxide, to make the solution that is your pop. Okay? And so why is water such a good solvent? It's because it's a polar atom. So what you get is oxygen's stronger, it's a bigger atom, and so it pulls the electrons. So it doesn't share very well. It is sharing its electrons with hydrogen, just not very well. And so hydrogen ends up a little bit positive. So you end up with your hydrogen side is a little bit more positive, and your oxygen side is a little bit more negative. So they're not really shared equally. So again, oxygen is stronger and more negative, and the hydrogen is weaker and more positive. And so the reason why that makes it a good solvent is because those positive side of the atom can attract negative ions or molecules and pull those things apart. And the negative side can pull apart positive charges, and the positive side can pull apart negative charges. So when we're talking about salt, the oxygens get attached to that sodium, and the hydrogens get attached to the chlorine. And so it literally can rip apart those atoms. So that's a kind of a cool thing. So almost anything that has even an imbalance of charges along that atom can make things dissolve. The other thing that polarity of the water atom molecule does is it gives what's called surface tension. Both of these images are images of surface tension. So we have this little insect that's kind of standing on top of the water. Sometimes they're called water walkers. And then here in this image, we see the swimmer is kind of encapsulated in this bubble of water. And that's because those positive and negative charges actually will work between water atoms, and water molecules. They get attracted to each other. And so you can kind of imagine this in 3 dimensions. They go up and down and side to side, and then they come toward and away from us. But at the top of the surface of the water, so there is no place for that other one to go, that other attraction to go. So they kind of double up along this top layer. And so that extra attraction is called surface tension. Another place you might have seen it is on like a water droplet that's like stuck to your fingertip. You can't get it to quite shake off, right? That would be because of that polarity and that surface tension and how water is kind of sticky. Another cool thing we look about water is how much water we have on the planet. So if we were to compare all the liquid water in the world to the fresh water, it would be this tiny little drop. So when we look at Earth's water supply overall, it's 97% salt water, it's 2% ice, and 1% fresh water. So we only have a tiny bit of water that we can actually use. So then if we start asking that question, like why are the oceans salty? Why can't we use that other water? It's because of 2 reasons. The first reason is because water's a good dissolver, it's a good solvent. It will grab stuff on its way down to the ocean. So that water comes down as rain, it gets collected in streams and rivers, and then all along the way it's picking up more and more minerals, and it flows down into the ocean. Well, then when evaporation occurs, and it leaves all of those dissolved things behind. And so then the process repeats itself. The other place it gets salt from is from cracks in the seafloor, where that molten rock can go directly into the ocean, that releases the temperature gets hot, and so it can dissolve more stuff in there, and then those are then trapped there in the ocean. And this part of the process, that those dissolved salts don't evaporate. So every time that evaporation occurs and we condense into a cloud, that's fresh, clean water until it picks up pollution, of course, but that first condensing bit, that is just pure water. Which then brings us, of course, to the quick review of the water cycle. In probably 6th, 7th, 8th grade, you learned about evaporation and condensation and precipitation and deposition and sublimation and all those different words. But notice how it's not really a circle. We've got evaporation that happens from plants called transpiration, and we've got percolation where it goes down into the ground and it might go into a water system down there, or it might infiltrate into the ground itself. All of those are different ways that water can move through its different phases on our planet. And I don't like the word cycle because it's not a circle. It's way more complicated than that. So we're going to take a look at this solid precipitation in terms of frozen water. Frozen water is kind of cool in that polarity of water makes water be very powerful force on our planet. Because of frozen water expands. And you might have seen this in ice cubes that don't seem to quite fit in their little spots in the freezer, or maybe you accidentally left a pop in the back of your mom or dad's car and it exploded. That'll happen too. So what happens is that polar arrangement of atoms will arrange itself in a much more orderly fashion when it turns into a solid. And we call that orderly fashion a crystal lattice. And so here you can see we've got 8 molecules, and here we only have 6. But notice how much this one takes up space that's a lot bigger than this space here. And so it literally expands when it freezes. This gives it a bigger volume, so this takes up more space, a greater volume, which decreases its density. So ice is less dense than regular water, so it actually floats. That's why your ice cubes float instead of halfway floating, halfway sinking in your beverage. It's because that water has expanded just enough to make that float. The other way frozen water makes a big difference is in expansion, in a process we call ice wedging. So here, this is why we get so many potholes in the spring. The water kind of seeps into small microscopic cracks, and then overnight when it freezes, it expands and widens the crack. Then the next day, more water seeps in, and the process repeats until you have pieces and chunks broken off. And so we would call that then ice wedging. And it doesn't just happen in roads and streets. That's how bedrock gets broken down. So here we see a great big boulder getting broken down. So it's not always your city's fault. It's sometimes just water's fault. But it's not just solid ice that can change our planet. There's lots of different ways. So here's a beautiful example of how the Colorado River carved the Grand Canyon, but it doesn't have to be quite that dramatic. It can be a little less so. So here's another river we can see that's dropping some deposits down and eroding other channels out, and so it will move sediment around. The cool thing about rivers is they make kind of a V shape. Notice how steep the sides of this are. And if we got down in here, we would notice it has a kind of pointy bottom right where the river is. Whereas a glacier, like this image, has more of a U shape. You can see that beautiful U right there as the glacier carves that out, again, because some of that is ice wedging, some of that is just the sheer weight of that ice as it moves down a mountain valley. And so it will carve out kind of a U shape. It will also leave deposits behind, and we can see that in our landscapes. So glaciers is another one. Beaches, probably the most extreme would be something like a tsunami, but we also have building up. So building up beaches that are getting created, we tend to think of as human beings as like, yeah, that would be a nice place to, go have a picnic and hang out on the beach for a while. But there's also destructive wave action along beaches where the water's really pulling that material down into the ocean and moving it along that way. And so these ones have a steeper bank and it has more bigger chunks of material. And so that would be a destructive beach. Probably my favorite, though, is caves. Caves are carved by that that ability of water to dissolve materials and to be a solvent. And so it carves the big holes in the underground, and then it can also, though, deposit, because it can deposit some of those salts or some of that material back down. And so we see these columns here. We see some stalactites back here. We see some stalagmites back in there as well. And so water can also be a shaping force. So why do we have to care about water? Again, water makes only a small amount of our overall water on our planet, and it's not equally distributed. So not everybody gets some. You'll hear that often, like when we talk about droughts in California or Texas, but also it happens on a global scale as well. And so here in America, we've passed the Clean Water Act. It started in 1948 as the Water Pollution Act, but then it was amended in 1972. It gives the EPA control over wastewater. So wastewater is anything that's had human use beforehand. And it also sets our water quality standards. Mainly one of the things it did was funded construction of sewer treatment plants. So before that, it was kind of optional whether or not you treated your sewage. So think about what comes out of your house in a day and put that in your local creek or river. Like it was not nice, right? But it also made it illegal for individuals to put pollutants in a water source. So this means that your family cannot put anything down a storm drain, because that storm drain goes into the Papio River system here in Omaha, and so that would be illegal. So you can't dump things down like oil or paint or anything like that, and you can't throw trash down there. It's not a garbage bin. So that Clean Water Act protects that. And a lot of times around Omaha, you'll even see like this is a drinking water area to remind people like, hey, don't contaminate this because this is going to go into your mouth later. The other thing the Clean Water Act did was said, hey, we can't solve everything. We can solve point source pollution. So it comes from one spot, a business, a home, something like that. But it can't stop what we call non-point source. So pollution that comes from lots of places, like salt from our streets, too many fertilizers from a farm field, something that runs off a parking lot, or maybe like even bits and pieces of junk that comes off of your roof. Those are things that the Clean Water Act does not protect, and individuals and communities have to do that on their own. So again, if we expand that idea of what wastewater is, again, wastewater is any water that's been used by humans. And so looking at this driveway here, you can tell you've got a car that parks there that's not very, not in the greatest condition, so it's leaking oil. If rain ran across this and picked up some of that oil, it would be considered wastewater because it's then had some sort of human influence on it. So it can include sewage and storm runoff, so that's why storm runoff counts here. Some of the biggest pollutants are nutrients, phosphorus and nitrogen, because they can impact the system. Once it gets into a creek or a river, it will cause an imbalance in that system, and it can cause fish kills and low oxygen levels and all sorts of stuff like that. And this image here is actually an image of Omaha's wastewater treatment plant. So if you've ever been down towards the airport, or maybe you played at Power Park, played baseball or softball down there, this is kind of near that general area. Other things that can be contained there are bacteria, viruses, and other disease-causing agents. There could be heavy metals that have come from the soils, like mercury, lead, arsenic. But then think about, do you take any daily medications for any condition whatsoever? Eventually you have to go potty, right? And then that potty then goes into our wastewater, and that gets treated. Those pharmaceutical drugs are some of the hardest to clean back out. So any kind of medication that you take is one of the things that is considered part of wastewater. And it's also problematic because once that gets into the system, we're not sure. You know, we do FDA tests on humans, and we try to figure out what implications that's going to be, but that's one of the things we kind of don't really know. Like, how is that impacting our environment around us? But also then personal care products, like the stuff you use to wash your face or your body, The stuff you put on your body, like perfumes and colognes, or any type of personal care product like that, that's all considered wastewater, and that's some of the things that it can harm both human health as well as wildlife. And again, rooftops, parking lots, salt from streets, all of that is considered wastewater. So what we're going to do in labs coming up is we're going to look at how that pollution, where that pollution comes into play, how much of it, where does it go, where does it end up, and we're also going to look at how that impacts groundwater, and how groundwater then is part of how do we use it, how do we get it, how do we get that to be part of that 1%. All right, warriors, have a great day.